The problem number 2 in the Physics Bootcamp addendum, it says if the position of an electron is uncertain to within 0.001 meters, what is the uncertainty in its velocity? Part 2 of the question says if the uncertainty of the wavelength of the electron is 321 plus or minus 0.0000048 nanometer, what is the uncertainty of its position? Okay, so this has to do with what is known as Heisenberg's uncertainty principle. Heisenberg's uncertainty principle, which was Heisenberg's explanation of the quantum nature of the atomic world, right, the quantum world. So he basically said that there are two pairs of conjugate variables. One is position, x, and its conjugate pair is momentum. Momentum p. And the other conjugate pair is energy and time. So time, which is variable t, and energy. And so what he stated the uncertainty principle in these terms: delta x, delta p greater or same as h bar over 2. Remember, h bar was h over 2 pi, so this is going to make it h over 4 pi. Okay? And the other conjugate pair is delta t, delta e is greater or same as h bar over 2 as well. So basically think of it like this. What the uncertainty principle is trying to say is if we try to nail down the position of an electron, let's say there's a particle and it happens to be an electron, and we want to know what its position is, right, to within very, very accurate knowledge. So what thought experiment can you think of to try to visualize where the electron is? Well, maybe we shine a beam of light on the electron, so in order to shine a beam of light, a photon has to come. Even if it's a very low energetic photon, just to be able to see where the electron is, right? That photon is going to come, hit the electron, come back, and it's going to enable us to see where the electron is, right? What its position is. But because the photon came and hit the electron, it bumped it, that's going to change its velocity, right? So by being able to observe the object, we have changed the velocity of the object, and therefore we have changed the momentum. Okay? If we don't want to touch it, we don't want to observe it, and we want to be able to do some other experiment, then we can find out what the velocity is, but then we'll have less knowledge of what its position is, right? So the uncertainty principle is limiting our knowledge of one of the two. Same thing here, energy and time, right? If we want to go back to the Big Bang and find out exactly what happened to the very, very tiny instance of time and nail it down to what is happening, our knowledge of the energy of the event is going to be uncertain. So the shortest amount of time within which we have the shortest amount of time for which we can have any kind of knowledge, that's called the Planck time. Planck time. And that's about 10 to the minus 43 seconds. Okay? So within an uncertainty of 10 to the minus 43, we can have a knowledge of what happened to the Big Bang. And so that is the delta t, right? And then that puts a limit on what our uncertainty of the energies involved in the Big Bang are, right? So all of these things are conjugate pairs, and it limits our knowledge of what is actually happening. In classical physics, you can always know what the mass and velocity of something is, what its position is, so you can trace it. That's because we are ignoring the fact of actually observing the object, right? But on the atomic scale, the observation itself affects the very state of the object, right? So in this case, how do we approach this problem? Okay, so in our case, we have delta x, delta p is greater or same as, and now we have h over 4 pi H is Planck's constant, 6.626 times 10 to the minus 34 over 4 pi. So in our case, somehow we have limited our uncertainty of the position to within 0.001 meters. Well, what does that mean? 1, 2, 3, that's 1 millimeter. So somehow we know that the electron is at a certain location. We have nailed it down, but there's a 1 millimeter likelihood of error in our knowledge. So it could either be here, or down here, or up there, or it could be out of the board or into the board, right? 1 millimeter this way, 1 millimeter this way, 1 millimeter. So that gives us a little room for error, right? Our knowledge is uncertain by 0.001 meters. So here's how we might write its position down. We might say the position of the electron is, let's say, at the 2 meter mark, plus or minus 0.001 meters. So maybe the electron is like right here, 2 meters away from the origin, but we are uncertain of its position by 1 millimeter, right? So what would our uncertainty of its velocity be, right? So what are we going to do is we're going to have delta x. Momentum is mass times velocity, and the mass is, we already know the mass of the electron, so we can have m delta v greater or same as 6.626 times 10 to the minus 34 over 4 pi. The mass of the electron is 9.11 times 10 to the minus 31. So the delta x is already 0.001. 0.001. The mass of the electron, 9.11 times 10 to the minus 31 kilogram. And the delta V, we don't know. 6.626 times 10 to the minus 34 over 4 pi. And now we take all of these things down there. Let's see what the answer comes out. 6.626 times 10 to the power negative 34. Divide that by 4. Divide that by pi. Divide that by 0.001 and divide it by the mass of the electron, 9.11, divided by 10 to the power negative 31. The uncertainty in its velocity, delta V, is 0.0579 meters per second. Okay, which a different way to say it would be 5.79 centimeters per second. Okay, so our knowledge of its velocity can be off by 5.79 meters per second. So let's say we knew that the velocity of the electron was pretty fast. So let's say it's, typical electron is going to be moving really, really fast. So let's say it's 200,000 meters per second. Okay, so it could be a very fast moving electron. That's already much slower than the speed of light, so we don't have to worry about relativistic effects. So then we would say our knowledge of the velocity is that the velocity is this with an uncertainty of 0.0579 meters per second, right? And so this uncertainty is not a big portion, a big ratio of its velocity. So we could still find out more or less what its velocity is, but there is a little bit of uncertainty. Now, what if we wanted to nail down the position even more? Like we want to know exactly where it is. Well, as this number gets smaller, 0.001, maybe we could say 0.001 nanometer. We want to know its position to within a nanometer, right? 0.001 nanometer. So what's going to happen? Well, then our uncertainty of the velocity is going to be what? We're going to have to multiply this by 10 to the power 9, right? Because the position is going to be 10 to the minus 9 here. It's going to go down on the bottom, 10 to the minus 9. And then that's going to go up to the top. Our uncertainty is going to be multiplied by a factor of 10 to the 9th. So what is our answer going to be? Well, take our answer, which was 0.0579 times 10 to the power 9, that's going to be 5.79 times 10 to the 7th. Okay? So our uncertainty is going to be radically changed. 5.79 times 10 to the 7th meters per second. That means our uncertainty is even more than the speed of the electron. The electron is going 2 times 10 to the 5th meter per second, but we are uncertain of that velocity to within 5.79 times 10 to the 7th meter per second. That means basically we have no clue what this electron is doing at all. No clue at all. That means our precision was too much. Okay, 0.001 nanometer was too much. So to be more realistic, we got to be somewhere in the middle, like 0.001 millimeter or maybe 0.001 micrometer. Then that is a little bit more doable. Okay, so now let's look at the second part of the question. And the second part says, what is the, if the uncertainty of the wavelength of the electron. So let's say we know that the wavelength of the electron is 321 nanometer, and its uncertainty of our knowledge of that is 0.000048 nanometer. What is the uncertainty of its position? So we can start again with delta x, delta p is greater or same as h over 4 pi, right? But this time, instead of momentum, we are uncertain of the wavelength. Now, how is momentum and wavelength connected? Well, we remember from de Broglie, we have linear momentum is the Planck's constant h over wavelength, right? So in the language of calculus here is, if we're uncertain of the wavelength by a certain amount, what is going to be our uncertainty of the momentum? Well, as it turns out, what we can do is take the differential of both sides here. Delta p is equal to negative h over lambda squared delta lambda. Okay? And then what's going to happen is we're going to have negative h over lambda delta lambda over lambda. And then this thing here is the linear momentum. So as it turns out, we have delta p over p is equal to delta lambda over lambda with a negative. Well, the only thing the negative means is that when the wavelength increases, the linear momentum decreases. So it's giving you the direction of the change. Okay? So what we're interested in is just the quantity, the magnitude of this here. So just take the absolute value. So what this is saying is a certain change or certain uncertainty of the wavelength divided by the wavelength is equal to a certain uncertainty in the linear momentum divided by the linear momentum. Okay? So delta p is going to equal what then? Therefore, delta p is going to equal p times delta lambda, p times delta lambda over lambda, right? So we could substitute that here. Delta x, and then in place of delta p, put p delta lambda lambda greater or same as h over 4 pi. Okay? And then now what? What are we going to do? Well, remember, we have here, this came from the delta p, which was p over lambda, but now we could substitute what p is. The linear momentum p of a particle is equal to Planck's constant over the wavelength. So I could substitute that here. Delta x, h over wavelength times delta lambda over lambda greater or same as h over 4 pi. The Planck's constant from here cancels with the Planck's constant there. Okay, so h and h cancel, and you end up with delta x, delta lambda over lambda squared. What I'm solving for here is what? What is the uncertainty of its position? So delta x is going to equal what? Greater or same as lambda squared is going to go to the top over there. Lambda squared divided by, and then I'm going to have delta lambda come down here. Divided by 4 pi delta lambda. Okay? So if the wavelength of the electron is uncertain within a certain amount, right? So this one has to be delta lambda. Delta lambda down on the denominator, right? So if this is the uncertainty of the wavelength, then the position is going to be uncertain within a certain amount. So if the uncertainty of the wavelength goes down, right? So if my knowledge of the wavelength gets smaller and smaller, and I'm very precise, then my uncertainty of the position gets bigger and bigger and bigger, right? So that means I'm uncertain of the position. So now let's put in the numbers. Square that, divided by 4 pi times the uncertainty, which is this number, 0.0000. There's going to be 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, 4, 8 nanometer. Now notice, as far as the units here, 1 nanometer is going to cancel one of the nanometer. Okay? And then I'm going to end up just squaring the 321, and then I'm going to have an extra nanometer on the top. Right? So let's calculate that. 321 squared divided by 4 divided by pi divided by all of these zeros. 0.00, there's going to be 5 zeros. 3, 4, 5, 4, 8. Okay, so that's going to be a huge number. Then I have an extra nanometer, so I have to multiply this by 10 to the minus 9 times 10 to the power negative 9, and I get 1.708 meters. Okay. Okay, so what is that? Well, that's quite a big uncertainty, right? 1.78 meter. That means my uncertainty of the wavelength was too small. I had too precise a knowledge of the wavelength, which caused me to not know its position by more than a meter, right? So now you can see how to do all of these kinds of uncertainties, different conjugate pairs. The main conjugate pair is the position and the momentum, and the energy and the time. But you could also have other pairs that develop out of that. This pair is the position and the wavelength. Okay? So now you can see how to handle those. Okay, thank you very much.